Okay, hi, I'm Bianca. Thanks, Elena, from the introduction. And tonight I would like to talk to you a bit about one of the phenomena that I'm working on as part of my research. And I hope that with the talk, throughout the talk, we can build a story to understand what I mean when I say too fast to stay, too close to escape. So to start our story, the first thing we need to do is to understand where the story takes place. And that place is very broadly our galaxy, the Milky Way, or in principle, any type of galaxy that's similar in structure to ours, which is a pretty common type of galaxy. To give you a sense of the scales, if we look at the left-hand side figure, the Sun, so our solar system, and therefore us, are located more or less of a distance from the center of about 100 millions of billions of kilometers, which, to just tell you how much, how big is it, is more or less 500 trillion times the Dutch coastlines. So it's a lot of cat bikes. But we're going to go a bit deeper than that, moving towards the center of the galaxy. So there are many components, and I'm not going to talk about them. What we're going to move is this golden area here, this kind of sphere. And within this sphere, there is a region called the nuclear star cluster, which is one of the most dense environments that we can have in the universe. And it can contain up to 10 to 30 million stars. It's very, very dense. And here we are moving slightly closer to the center to only 200 billion satellites. If we move further inside, we find Sagittarius A star. Sagittarius A star is a supermassive black hole. And a black hole, you can think about it as like a heavy weight with such a strong gravity that anything, matter or light, if they come too close to it, they're not going to be able to escape anymore. So you can understand it is a very weird and very interesting environment. And here we are very close to the center, so we are about 26,000 cat-bikes. But the influence of the black hole and its strong gravity extends much further than the center, so it extends through the nuclear star cluster. So Sagittarius A star has 4 million times the mass of the Sun. And all of this mass is included in a region which is smaller than our solar system. So you can understand how tiny and how special this environment is. And this is the place where our story will take place. To understand who's going to be the main character, we need some ingredients. And the first is going to be Sagittarius A star, so in general any type of supermassive black hole. Then, which I'm going to shorten as BH, so if you see a BH, any time it's going to be a black hole. Then we need binary systems. Binary systems are any type of systems consisting of 2 objects, which can be 2 stars or 2 black holes, that are locked together by gravity, and they revolve together around a common center, around each other in a sense. The third ingredient are gravitational waves. Gravitational waves are ripples in the fabric of space-time, so in the fabric of our universe. And you can, they are generated, so are perturbations in the material that builds our universe generated by masses that are accelerating. And you can think about them with an analogy, thinking about when you toss a rock into a pond and you see the ripple on the surface of the water. So if we now start to combine the first 2 ingredients, we can build a binary where one of the objects is a tiny black hole, more or less 10 times heavier than our Sun, and the other object is Sagittarius A star. The tiny one is going to revolve around the big one, and this object is made by 2 things that have a very big difference in mass. So one is much heavier than the other one. So we're going to call this an extreme mass ratio binary, let's say. What happens in this case is that the tiny object is going to revolve around the big one, and every time it gets closer, it loses energy, emitting gravitational waves. And as it emits gravitational waves, its orbit is going to shrink and becomes tiny smaller. and then it's going to pass again next to the black hole, and emit more gravitational waves, and the orbit is going to shrink a tiny bit more. And you can think about this as when you throw like a coin in a sink, and the coin is going to start slower, and then fast is going to sink into the hole. In a similar way, our tiny black hole is going to, in the end of all of these emission of gravitational waves, sink and plunge into the big mass. And this is called an in-spiral. So altogether, this is called an extreme mass ratio in-spiral, and this is the character of our story. So to more or less visualize it, this is an idea of a tiny black hole, okay, spinning around a bigger one, and the waves that you see around are the perturbation of space-time. And as it gets closer, you see there is a sort of burst in the emission. And if we can span a bit further, we can go with we cannot. Okay. Okay, nice. So in the end, it's going to get closer and closer. The emission is going to get stronger until the point where you can see here in the small figure, they're going to merge together and form a blob, basically. Okay, now the question is, how do we get the tiny black hole to arrive so close in the galactic center to be affected by the gravity of Sagittarius A star? And there are various ways. I'm going to talk to you about two of them, which are the ones I'm touching upon during in my research. The first one I'm going to refer to as the classical scenario, just because it's the one that's been more explored in the literature. And in this case, you can start, imagine we have a tiny black hole, and we have a very dense environment, like the nuclear star cluster I talked to you about before. So a lot of stars. And the tiny black hole is moving among these stars, and it's going to feel, every time it gets closer to one of them, the pull of the gravity of each of the stars. And every time it's going to get a tiny kick. You can think of it as like walking through a room which is very crowded of people, and you want to get at the exit of the room. But every time you get like a shoulder kick from someone, and slowly and slowly and slowly, at the end you find yourself at the center of the room. In a similar way, the black hole, feeling the pressure of all of the other stars, is going to end up in an orbit that brings it to the center of its system, which is the big Sagittarius A star. So these encounters are called gravitational encounters, because they are driven by gravity. And this phenomenon is called two-body relaxation. So this is one way of getting a tiny black hole to pass very close to the big one. Another way is called the Hill scenario, by the name of the astronomer who discovered it in 1988. And the idea is this: we start with a binary, and the binary is on an orbit that can get close enough. What happens is that the force of the black hole, which in this case takes the name of tidal force, acts on the binary in a similar way as the moon can act on the Earth. So gravity is going to affect this side of the Earth, the closer one, in a stronger way than the side that is further away, pulling the waters, creating tides. In a similar way, the black hole is going to pull one side of the binary, the closest one, and stretch the binary. And since the gravity is strong enough, it can actually manage to stretch the binary enough that it breaks it up. And if the binary is broken up, what happens is that one of the two objects, maybe stars or black holes, is going to be stuck here, rotating around Sagittarius A star. So it's going to be too close to escape. And the other one is going to be ejected, so pushed away outside the galactic center at very high speeds, and therefore it's going to be too fast to escape. And about this second star, you will hear in the second talk. So now we have two different possible ways that are not mutually exclusive to get a black hole very close to the galactic center. But well, it's okay. You can figure it like something like this. So you have the big black hole there, and the two stars start arriving together here until the point where they break up. Now, how can we distinguish between these two channels once the black hole is there? Why it's important to distinguish among the way we get a black hole in the galactic center? The reason is that we are going to deposit our tiny body on a slightly different path. And this slight difference is quite important. And the reason why is, with the classical scenario, we're going to deposit the black hole on a path that is more stretched with respect to the other case. The fact that it's more stretched means that the tiny orbit, the tiny body, can get closer in the point where they are the closest possible than in the Higgs case. So this distance here is bigger than the other case. Once the black hole arrives so close, it feels the gravity of the black hole more, and therefore it's going to emit more gravitational waves. So the closer the passage, the more is the emission, and therefore evolve faster. And it's going to evolve faster until it plunges, and this is going to happen faster than in this case. Because here, being more further apart, the effect of the black hole is slower, so it will need more passages to emit the same amount of gravitational waves. And this is very important because if we want to observe something, so if we want to actually see these extreme acceleration spirals, the fact that these stay there for longer can enhance our chances of seeing them. But the question is, how can we actually hear these waves? How can we see and know that this phenomenon is actually real? We can use these. This is called LISA, is an acronym for the Laser Interferometer Space Antenna. It's a joint ESA and NASA mission that's going to be launched in 2035, and it's the first detector of gravitational waves based in space. It's quite cool. It's something like this. So it's made up by 3 spacecrafts, and at the center of each of these, these 3 spacecraft are going to orbit on a certain orbit around the sun. And at the center of each of these spacecraft, there are 2 cubes of gold and platinum that are located at a certain distance among each other. When a gravitation, so we have the 2 golden cubes in each of the spacecraft. And the 3 spacecraft are shooting laser beams to each other. And this configuration, this triangle, is going to move around the sun. These laser beams are arms that are long 2.5 million kilometers. So it's a massive, massive telescope. It's something you cannot build on Earth. So it's going to be very cool. When a gravitational wave passes by, what happens is that it's going to perturb the space, so stretch or squeeze the space between the 2 golden cubes. And this is going to affect how the laser beams are going to receive and send among the 3 spacecrafts. So by detecting this shift due to the passing of the gravitational waves, we can know that something has passed there. And then based on frequency and characteristic, we can try to understand what the source was. So the idea is that LISA, being so big, is going to be powerful enough to actually hear extreme acceleration spirals that are quiet sources. So sources that we couldn't detect with the current ground-based telescopes. So, okay, let's assume we actually are going to, in 2035, hopefully, see these MRIs, these extreme acceleration spirals. Why do we care? The reason why we care is that the black hole is a very specific environment, and is the environment where gravity takes place in its strongest form. So if we can see these extreme acceleration spirals, we're going to be able to probe gravity in this region and understand if the theories we are using to model and explain gravities are actually correct and accurate. We can discover more about black holes, and we can discover more about the population of objects in our galactic center. Why? Because if we know, if we find many of them, then for instance it can mean that there's going to be many binaries in our system, and it can inform us on the type of binaries or stars or populations that we have in the galactic nuclei, which is a region where it's very difficult to look. And since our galaxy is a common type of galaxy, then we can extend these to other galaxies. So I think it's quite interesting. So this is just the summary. So I hope I convinced you that finding extreme mass ratio in spiral and possibly seeing them with LISA will allow us to discover more about extreme effects of gravity and galactic nuclei.
Thank you, Bianca. So we have some time for questions. Actually, I have quite a bit of time for questions. So yeah, go ahead.
A question: are there also other ways to observe this phenomena?
So directly, LISA for now, as far as I know, and there are some alternatives to LISA, some space-based telescope, Chinese versions of LISA. So I think this is one way. I think there's going to be indirect ways of probing them, possibly. There are some phenomena that are related. So I think by probing them, we can indirectly say, okay, if this other thing happens, then extreme mass ratio in spiral have to happen as well. But I think directly LISA is going to be, at least for now, the only way. Because they are very, very faint. Like they emit waves at very small frequencies.
Thank you.
I was wondering what's the reason behind the emission of gravitational waves in the close past-time? I think I've seen it before.
Yeah, it's you can think about it as so due to the effect of gravity, you can think about it as the object is losing energy, and since energy is overall conserved, this energy is going to go into a perturbation of the space. But I don't know if this is what you were asking.
Yeah.
It's like any mass that accelerates is able to release a certain amount of energy, and that energy cannot just get lost. So you can think about it as it's like propagating through space-time.
Yeah. Do we already know if we have this mass ratio in our galaxy, or are we looking for it?
We know the mass of Sagittarius A star is about 4 million times the mass of the Sun, and we know that there should be black holes of the order of 10 solar masses. So we actually expect to see and be able with LISA to have extreme mass ratio in spirals. One thing that is not certain is what type of binary system do we have in the galaxies of star and black holes. So it's a bit difficult to predict how many are we going to see, which is a full area of research, and I think it's what people are going to try to prepare before LISA actually gets the data. But these masses are there.
Yeah, very interesting. It's a long shot maybe, but this instrument has those 2.5 million kilometers arms. Why not 5? Why not 10? Did you have any idea of why we stopped at 2.5?
So, this is a good question. I don't know. My guess is that there are limitations intrinsic in the observations. I guess you need to place the 3 spacecraft in orbits that are not going to be perturbed by anything else. So I imagine that the risk of getting longer arms is going to be that there can be other sources of noise, or I think the noise is going to probably be bigger because you're going to span a bigger region and more things can get in the way of obscuring your faint signal from the gravitational waves. But I don't know why exactly 2.5 and not 3.
What's the time scale like it takes for like when the mass ratios, extreme mass ratio spiral starts to when like the star converges into the black hole, like for the classic scenario versus the Hill scenario? I guess like how long?
You mean in terms of time?
Yeah.
How much time does it take?
Yeah, for like star.
So this depends a bit on how stretched or how circular your binary is at the beginning. But for instance, for a binary which is not perfectly circular, more or less the full emission of gravitational waves until the plunging, it's about 100,000 years, so it's a long time. And the other mechanism, so when you have the tiny kicks, that's even longer. It can be up to, I'm trying to do it in, it's like 100 million years. So it's very long scale. So in a certain way, these are also going to be some sort of like fossils. So something that started a long time ago, and we can see it.
You showed this Hills mechanism, but presumably that needs things already to come in on quite an elliptical orbit. So do you expect the two-body relaxation to be important in setting that up? And in that case, is there a kind of predicted ratio between the two-body relaxation frequency and the Hills frequency, just based on the fraction of binaries that you'd expect in the galaxy?
So it's true that to bring a binary that close, for instance in the work I'm doing now, to bring a binary that close, we are still invoking two-body relaxation. So instead of acting on a single star, you act on the full binary system. I think expected rates for two-body relaxation, I think is 10 to the minus 8, 10 to the minus 9 per year. And I think Hills is a bit less explored, so the literature goes back to 2005. But I think the rates are a tiny bit less, so it's 10 to the minus 7 per year. But I think this is still, it depends, because we don't have a good knowledge of the population of stellar binaries, because these, I talked about black holes, but in principle the binary can be two stars. And through the life of the star, the one that is deposited is going to become a black hole. Or they can be black hole binaries, but we don't have a good certainty of what type of binaries and how many of them we have. And we know even less so about black hole binary. So these are estimates. I think the Hills should dominate what we see in LISA, but it depends on how frequent the relaxation is.
So LISA always seems like a crazily ambitious project to me, with these different things so far apart. Do you have any idea how difficult it is? What's the most difficult part, and how difficult is it going to be to realize this in space?
Like to build it?
Well, yeah, or to calibrate it. What precision does it need to have in terms of arm length?
So I can tell you the tiny things I know, because I'm not an observer and I'm not an experimental person. So I think the lasers and the spacecraft are going to move on geodesics. So the two masses are going to be in free fall. So they are going to be kept there, and the spacecraft just acts as a sort of like ensuring that over time this is not going to get too far. The mission should go for, once it's launched, for 4 years. So I imagine this as plays a part in like knowing that it's going to be stable and reliable until then. I can tell you that they expect a lot of noise, and the fact that there's going to be many sources overlapping each other, so it's going to be very difficult to distinguish what is what. But on the technicalities of building it, honestly, I don't know. I'm sorry.
Would having multiple visas help with figuring out what comes from where, or would that only make things worse?
I mean, there's going to be another, which I forgot actually before. There's going to be another like space probe, which is actually using pulsars in like a triangular shape, is the pulsar timing array. About LISA, I would imagine probably yes, but I think this is already extremely expensive. It's like 500 million billions, I don't know. Like it's gold and platinum in the tiny cube. This for me is absurd. So maybe you can try with it and NASA.
Do we know what kind of, sorry?
Oh, no, go on.
Do we know what kind of, what the signal of these binaries would look like, since you said it's like very small signal, so would you be able to pick it out from noise easily, or?
Well, no, easily no. I think
Yeah.
we have, there is an idea of what kind of frequencies MRIs are going to enter. So while they are building the instrument, they're also thinking about what they're going to see and considering their noise level, if they can actually see things. So MRIs should be something you can see. It's going to be very difficult because while the black hole inspires, its orbit is changing, and it's changing how much is stretched or elongated or circular, and this is something you need to model. If once you receive a signal, basically you see a wave, and you need to have a theoretical model with the form of wave, and then you can match them and think, oh, this is actually what I expected for MRIs. This part is very difficult for MRIs because they change. And they have many different eccentricities among time. So it's very difficult to predict what form they will have once they will enter the frequency range where LISA can hear them. But it should be possible. In the LISA science document, they are confident that it should be something we can see. And I mean, there are sources which are emitting much stronger waves and sources which are emitting a bit less. I think it's a region where there's going to be some overlap, but I think it should be possible, and there is time until 2035.
Okay, so one question there, maybe then we will stop, or I will allow maybe another one, let's see. Go ahead.
Yeah, thank you for the interesting talk. I was wondering, when can we expect the first results from LISA?
So, in principle, if everything was up to time, it should be launched in 2035 and should be active for 4 years with the possibility of extending it to 10 years if everything goes to plan. So it will depend, I guess, on how long they are going to actually keep data. But I imagine after the first, I don't know if they need to wait for the 4 years, or I think probably after a year they're going to already start analyzing part of the data. I think there's going to be gradual releases of data as any other instrument, I imagine. But let's see if it's going to launch in 2035.
All right, any last burning question from anyone? Yes, let's go. That's one.
You said it's going to be 4 years in space, LISA. Do you think we would actually see some change in the orbit with such a little amount of time?
In the orbit where the triangle shaped...
No, the orbit of the binary, the extreme mass version.
Well, I think the idea is to... so, if you see a certain signal with a certain frequency and a certain shape of your wave, then you can think, okay, that was an extreme mass-ratios spiral. But this doesn't mean that we need to follow the binary evolving for 10 to the 5 to 100. No, we're just going to say, okay, this looks like an MRI, so with this we can assume what happened in the past, and we can follow it possibly until the moment when they merge. But we are not going to follow anything for the full evolution. So, yeah, the idea is to hopefully find them before they merge.
All right, then let's thank Bianca.